when it's very difficult to help somebody when they start the lab on the day it's due and they're having lab equipment issues, or they're not really sure how to use the equipment. So please, for this lab, you need to start early. If you don't, really it's on you. It's all your fault that you didn't start early on the lab, okay? I just want to let you know that. So we're basically going to look at a circuit and circuits that we discussed in lecture already. If you go back and look at the PowerPoint or the class slides from chapter 28, you will see a circuit that looks like the one you see now on the screen. Okay, except it was, I set it up in the class notes in a diamond shape. Okay, but it's really the same circuit. And so you're going to build this circuit and you're going to make some measurements. You're going to be measuring the current through the battery. Again, use the ideas that you learned from the multimeter quiz to make the current measurements. Ideally, you'd like to measure the current through R1, through R2, through R3, through R4 with the multimeter, but it's cumbersome to do that. And so what I'm going to have you do is to measure the voltage drop across those 4 resistors and then divide by the resistance to obtain the current through each resistor. So let me show you what I've done basically. I actually, on Sunday, I built the circuit. In fact, let me change the view so it's easier. I built the circuit and I put it on a breadboard. Okay. And this is essentially the circuit that I built. This is the circuit in the lab. And I taped the adapter to the breadboard so then I could then connect and disconnect the power supply. You're going to set this to 6 volts. And then you can plug this in so you don't have to do any voltage adjustments. Okay. I just feel that this is fairly convenient. Yes, it's high-tech. And the tape comes with your kit because there's a lab called a DC motor lab. In there there's a electrical tape. So you can use that tape if you want to. It's up to you how you want to do this, but this is how I did it for convenience. And I was able to make all the measurements. And you can use wires like this, for example. I don't know if you can see the red and the black wire. They're sticking up, and I can use that to make current measurements. I can break my circuit as needed to make the current measurements. Okay. The values of R1, R2, and R3, and R4 are given, so those are the values you want to use in the right locations. Yeah, if you have your own power supply and you want to set it, just set it to 6 volts, that's fine. Okay. So it's, again, this is a lab 1 wiring circuits, but also doing data analysis. So in part 1, let me draw the circuit. Let me change the view here. That's R1, R2, R3, and R4. And you're told what R1, R2, R3, and R4 are at the beginning of the lab. So I expect you to use those values. Okay? R1's 100 ohms, R2 is 1,000 ohms, etc. Okay, so what happens? So you have the current from the power supply, which I call I1 plus I2, go here, and then the current splits into I1 and I2. Okay? And so what you're going to do is you're going to determine I1. I1 is going to be and I2 and then the sum, which is the IS, and you're going to measure IS with the multimeter. And you're going to compare this measured value to the sum of these two currents. And you're going to see whether they agree or not. That's what you'll be doing in part one. Now, let me show you the data table for part one. Let me expand this. That's the data table for part one. So you notice you need to know R plus or minus delta R. You need to know V plus or minus delta V and I plus or minus delta I. Now, I plus or minus delta I is going to be calculated. How are you going to get the uncertainty for the resistance? You could use the last band of the on the resistor, but since you can measure the resistance with an ohm meter, why don't you measure it directly with the ohm meter? But then, how do you get the uncertainty using the ohm meter? Well, you're only going to measure, yeah, you can, but we're going to do it the easy way. You can measure the resistance 10 times and then get a standard deviation, but I'm going to make it a little bit easier for you. Yeah, you look at the last digit. Well, what you want to do is really not only look at the last digit, but look at to what decimal place the measured value varies to. Okay? So when you use these multimeters, and I'm not sure where I put my multimeter at. Oh, here it is. You can see there's not a lot of equipment for this lab. You're going to use your two multimeters, this board with the little resistors on them, and the power supply. When you measure the resistance with this multimeter, you're going to see the last or the second to last digit vary. So base your uncertainty on what digit is varying on your display. Does that make sense? And when you're measuring resistance, because most of you folks don't have alligator clips, that's going to be tough to measure and because of the fact that you don't have good contacts. So what I would do to measure the resistance is I would actually put the resistor into the board and then try to use these leads and make good contact with the resistor. Okay? So it doesn't vary as much, because when you're holding it in place, your hands move, the contact between these ends and the resistor is not very consistent, and you'll see a fairly large variation. You're also going to be measuring V and delta V. And delta V, again, you can get by the uncertainty you can get by looking at the variation of the last digit. Is it going to vary to the thousandth place, the hundredth place, or the 10th place? That's what you got to ask yourself. Okay? And it also depends, and the uncertainty is going to depend on what what scale you're measuring, right? Because there's a 2-volt scale, a 20-volt scale, etc. Questions so far? Of course, since you know the uncertainty of these two, since you know the only problem right now, I'm going to have too many deltas. Then you can figure out what the uncertainty in I1 is, right? Delta I1, using the methods of air propagation. This is where using the delta symbol gets annoying. There's two deltas there. Okay, you guys and you folks remember how to do this, right? From Physics 205. So you're not going to get away from it. You're going to be doing this a lot in this lab, and you're going to show your work. And remember, you not only need to show me the equation you use, but I need to see the numbers you put into the equation. So, but you don't have to show me. You're going to have to do this calculation a lot of times. I think this particular calculation for table 1, you'll do it 4 times. Okay? You only show me 1 of them. Don't show me all 4 of them. Okay? Unless you're a glutton for punishment, that you can show all 4 of them. Okay? And I need to see not only the equation, I need to see the numbers you put in. Because you might have the right equation, but you might put in the wrong numbers. Does that make sense? And then once you know delta I1 and delta I2, then the delta IS that you calculate can be written that way. Okay? And of course, the delta IS that you measure comes from the variation in the last digit. Now remember, that different current scales will change the resistance in your circuit. Okay? So different values, you're going to change the resistance of your circuit based on what scale you use here. And I recommend, because you can get an extra digit with this guy, I would recommend using this to measure current. And I made a mistake, I think because my eyes are getting bad. The little meter actually can measure voltage fairly accurate, voltage and current fairly accurately. So for some reason I couldn't see one of the scales on the little meter, but it's actually pretty good. But this one's better because this gives you an extra digit. So use this to measure current, and then use the little meter to measure voltage. Okay. And the question to ask yourself, should I leave the meter in while I'm measuring the voltages? Okay. So one of the things I did when I did this lab, by the way, I took these pieces, these wires here, and what I did was I actually taped them to these leads. I used electrical tape to tape them to those leads, so I can actually take the leads, put them in the proto board to make the measurements. And then I would set the leads on a table so these things don't move around. Because when you move them around, that's going to change your measurements. Okay, and unfortunately, we don't have alligator clip leads that fit on the end of this. Questions so far? No questions? Okay, so in part one, then once you've done your calculation, there's some questions you need to answer. You will try to verify Kirchhoff's current rule or Kirchhoff's current law, and you're also going to try to verify Kirchhoff's voltage law. Just choose one of the loops that you see and see if the voltage law is verified. For example, I can choose this loop and see if this drop plus this drop plus this drop equals 0. And don't forget to talk about errors. Okay, when I ask, do your results, does your results agree with Kirchhoff's voltage law? You have to take into account experimental errors. Okay, so you can see there's a lot of error analysis in this lab. There's a lot of error propagation in this lab. There's a lot of questions regarding, whether values agree or not, or does your data agree with your theory? And so this is going to take a little bit of work because your error analysis takes a little while to do. Of course, since this calculation is repeated over and over again, you can always create a spreadsheet. In Excel, I just put numbers in and the Excel spreadsheet will calculate it for you. I don't know if you have experience with it. I will at the end of the semester when we do the LRC lab, go through and talk about how to do calculations with spreadsheets. But if you have questions on them now, I can always show you how to use a spreadsheet to do calculations. Okay. Questions? You guys seem awfully quiet after the exam, I guess. Okay. In part 2 and 3, or actually part 2, what you're going to do is, let me change views here. Okay, so I see that we lost internet connection. So let me wait for a second until we get the internet connection. All right, so in the second part of the lab, what we're going to be doing is we're going to place an ammeter between points A and C as you see in the circuit. In the previous case, there was no ammeter between points A and C, and so the potential difference across A and C in that particular case was not 0. Once we put an ammeter between A and C, assuming an ideal ammeter, or assuming the resistance of the ammeter is low compared to the resistance of the rest of the circuit, points A and C are going to be at the same potential. And when you do the lab, you can actually test this to see that, okay? So we're going to look at how much current goes through between points A and C. So this circuit's a little bit different. Again, this is a circuit that I analyzed in class. So you want to go look at the video on the chapter 28 lectures and go over the problem I did in class. I have this problem, I did this problem in class. Okay, so you can go over the video and look at the analysis for this circuit. So in this particular case, if points A and C are tied together, then R1 and R2 are in parallel. R3 and R4 are in parallel, and those two combinations are then in series with each other. So what you're going to do in this particular case, let me switch views. Is you'll put the ammeter here, and as you're doing the measurements, this always has to be there. Okay, for every measurement that you make here, this has to be there, because otherwise you change your circuit. If you take this out and then make these measurements, you're changing your circuit. This has to be there the entire experiment in part 2. Okay. This one doesn't have to be there. Otherwise you can't do the experiment. You can't make the measurements. This one always has to be there. And so this is going to be the good ammeter, of course. And you'll use the smaller ammeter to measure the voltages. So you'll measure the current, and then once you measure this current, you take this out of the circuit because you don't have enough ammeters. Okay? So when you get to this point here, you're going to have current split. And then this ends up being I3 minus I1. Okay. And this current is going to be I2 plus I3. So you can calculate this current either by knowing this current, this one and this one, or this one and this one. So you're going to go through, measure this current, measure these voltage drops, and then fill out this data table. So you will calculate I1, I2, I3, I4, and the associated uncertainties. You also need to note the scale reading when you're measuring the current between points A and C. And the reason why is because you're going to do this measurement twice. You're going to do this measurement with the highest current setting possible. And then you'll do it again with a lower current setting. So for example, if you can do this measurement on a 10 amp scale, then do it. Otherwise, do it on a 200 milliamp scale. Then for the next case, for table 3, try to do it for a ammeter setting that's can measure lower currents. The goal here is to see the effect of the resistance of the ammeter in your measurements. Okay, that's the goal, is to look at the effect of the resistance of the ammeter in your measurements. And you might say, how can I measure the resistance of the ammeter? That's actually pretty straightforward. So if I want to measure the resistance of this ammeter, I can take 2 cables, one for the milliamp and then the other one for the common, and then I can go and connect, use this one to measure resistance. So I use the volt, ohm, and then the common. I turn this on to measure resistance. And then I turn the big one on to measure current. and I'll get a value. Okay. So I'll get a value for the resistance. That's what you do, and then you can change the setting. You can change the current setting, and you'll get a different value for the resistance. Okay, so and that gives you an idea of the difference. You know what the effect will be on your circuit. Okay, let me turn these off so I don't waste the battery. And again, you're going to be doing the air propagation. And again, if you have questions regarding air propagations, don't hesitate to ask. So after table 3, you have questions, right? So if you look at the lab, you have table 2 where you collected the data with the meter between points A and C, and then you'll do it at a different ammeter scale setting, so you can see the effects of the resistance of the meter. Then you have a couple of questions. You actually have a bunch of questions. Now the last question you have, hold on a second. The last question you have out of these 6 that you have here, ask you to derive an equation. I expect you to use the equation editor or some sort of equation editor to type that derivation in. Do not handwrite the derivation. Okay, do not handwrite the derivation. Okay, all your calculations, everything has to be done, has to be typed out. So use the equation editor that comes with Word or some other equation editor that you like using, but it's got to be typed out. And anytime you do a derivation, it's actually a good idea to explain what you're doing in the derivation. And imagine if your textbook had no explanation of the derived equation. How would you learn from that textbook? Okay. All right. So really, this is it for the lab. And procedurally, it's not a hard lab because all you're doing is, let me go way back. You're wiring circuits and you're either measuring voltages or current. And if you want to play around with the meters, you can measure the resistance of the ammeters at different current settings. And I actually encourage you to do that so you get familiarized with the ammeter, with the meters you're using. You can also try measuring the resistance of the voltmeters and see what you get. That's why you get familiarized with the meter. Don't forget, you know, your meters have come with instructions. You should read the instructions, okay? Again, also to get familiarized with the meter. This is what engineers do when they have a piece of equipment. They have to learn how to use it. They got to read the instructions manual. That's what they're there for, okay? So I wanted to talk about one more thing, and then I'm going to use next week. Hopefully the internet will work better for me next week. I will use next week to answer questions you may have on the lab, okay? I want to talk about these resistors. They come in different sizes. These resistors come in various sizes. Okay. By the way, notice how I have the wires here. I actually put those wires in to measure my current between A and C. I actually taped the leads to the meter so that I can measure between the points A and C by doing this. Anyway, so the resistors come in different sizes. You know, you'll have or you might have a really thick one like this. They have the color code. The different sizes represent how much power they're rated for. So the different size resistors They indicate different power ratings. So they go in increments like 1/4 of a watt, actually 1/8 of a watt, 1/4 of a watt, 1/2 watt, etc. That indicates this is the maximum power you want to put into that resistor before it starts heating up. If you go above these ratings, the resistor will start heating up, and then that resistor will not obey Ohm's law anymore. And you can figure out the maximum voltage you can apply because, this is going to be equal to delta V squared over R. So you can figure out the maximum voltage you can apply. So one of the things that we're not doing in this lab, just because of the limited power supply, if this lab was done on campus, I would actually have you set the power supply to the maximum voltage you can apply to the circuit. Because I would have you figure that out. Okay. So, one of the questions one can ask, for example, on an exam is, what is the maximum voltage I can apply to that circuit? And you had a similar problem in the previous chapter involving capacitors. Okay, same idea. I mean, if you design a circuit, what is the maximum voltage I can apply here so that I don't burn any of the resistors? Because if you put too much voltage on these resistors, not only will it get hot, it'll start smoking, and then it'll turn black. Okay, so you do have to consider the power ratings of your resistors in your circuit. Okay, like I said, if we were doing this class, if we were doing this on ground in the classroom, I would probably have you calculate what voltage you can set to, and then you would set it to that voltage. But because we're doing this at home and we don't have completely variable power supplies, I'm not asking you to do that. But it's an important consideration for you. Anytime you're working with resistors, you have to know the power rating of the resistors. Now, this equation is just for the single resistor by itself, but then you have to be careful when you hook these up in a combination, because just like the light bulbs, these things are not going to get, they're not all going to get the same voltage drop across them. There's going to be one that's going to be a weak link, and you just don't want to go over the maximum for that weak link. Otherwise, that one will go bad. Okay? So just something for you to be aware of. It's something we're not doing here because the class is online, but you should be aware of the power rating of the resistors. Okay, so really that's all I have for this lab. I think most of you folks are familiar with how the labs were done in Physics 205. You will be doing the error analysis. You will be typing in all the equations, etc. So I'm going to end it here, and I'm hoping that you all come up with questions next week regarding this lab. And again, I apologize for the fact that the internet went down. Okay? So we'll talk to you next week.